Welcome to the second part of chapter 20, where we are going to take our charge model that we talked about in the beginning in Coulomb's law and how, like charges repel and unlike charges attract each other, so a positive and a negative tend to go towards one another, and that there's this force between charges according to how close they are and how much charge each one carries, which led us to Coulomb's law. What we're going to look at today is how charges tend to change the space around them in order to affect one another. And so what I've got here is a positive charge where my mouse is, and you can see as I move it all around, there's all of these arrows that get affected by that, right? And then when I take my negative charge up here and I move it around, well, that affects the arrows too. And they do this in different ways. Before you continue on watching this lecture, I would like you to complete the electric field of dreams activity that you see in D2L that kind of investigates these relationships. But in this lecture, I'm going to come back to this demonstration to kind of show you what I'm talking about. So just like light waves had both the ray model and the wave model, models are just ways that we can kind of think about or conceptualize these bigger ideas in physics and in science in general, right? And so when we talked about light, there was the ray model versus the wave model. And now when we're talking about charges or electricity, because the two are intimately related, you see T-R-I-C-I-T-Y, there is the charge model, where we talk about things as kind of these chunks of positive or negative, and we know there's forces between them. But then there is also the field model. And the field model considers not just the chunks, but the space around them as well, and how they affect one another. And so today we are focusing on the field model, which is really kind of an extension of the charge model. There are field models in all kinds of science, and so this is something, a general field model, right, is where an object affects the space around it. And so there are gravitational fields, there are magnetic fields, and there are electric fields. You are probably pretty familiar with the magnetic and gravitational fields. This one you feel every single day, and then if you've ever used a compass, then you've used our magnetic field of the Earth as well. And probably in your primary schools you studied magnets and kind of how they work. But we're going to extend this idea of something affecting the space around it onto charges and electricity. And you can think about this a lot like a magnetic field or a gravitational field. And we'll learn the rules for it. Right? And so in electrics, we have the charge model, where we think of these kind of chunks and they have forces on each other. And we use Coulomb's law. That was all what last lecture was about. Or when we consider electrics, we can think of the field model. And so the field model, we begin to talk about this electric field, right, which we will represent with the symbol capital E, and kind of how it's affected as we move these charges around. So a couple of things to know. Electric field is measured in newtons per coulomb. And so when we talk about the electric field, we're kind of talking about the amount of push or pull that an electric charge might have per coulomb of charge that it owns. Electric fields are vectors, and so one of your jobs, just like with velocity and acceleration, is to decide, based on your situation, is this electric field pointing up? Is it pointing right? Is it pointing down? Is it pointing left? And just like any other kind of vector, electric fields can be added. And so if I have two charges and their electric fields are going to the right, well, then those stack up and add to each other. If I have two electric fields and their electric fields are pointing in opposite directions, well, I subtract, and whatever the difference is the net electric field, right? And then kind of as a subset of this, and it's going to help you figure out the direction that those fields move, they move away from positive charges and toward negative charges, right? And so when you're drawing, right, a positive charge always has the field moving away from it, and a negative charge always has the field moving towards it. This will be very, very important. So field goes from positive to negative. Right? We do have a couple of formulas to help you calculate the strength of the electric field. So at the bottom of this slide, the formula on the left, we can think about the electric field as a force that some charge experiences, and then the charge of that charge being affected. So if I have like a +1 charge, +1 Coulomb charge, that has a force of 3 newtons on it, then I would talk about the electric field being 3 newtons per Coulomb, or 3 newtons per Coulomb, would be the electric field there. If I don't have that information, I can also think of it as the electrostatic constant. It's kind of this abbreviated version of Coulomb's law. The electrostatic constant, the absolute value of that charge, and the distance away from it. And so just like the gravitational field, as you get farther and farther from a point, the electric field is going to get weaker and weaker, right? As I get farther and farther from the Earth, the electric field gets weaker and weaker. As I get farther and farther from a magnet, the electric field gets weaker and weaker. And so just a little representation here about how to draw electric field lines and kind of what they mean. Right? And so first and foremost, electric field lines always go away from positive, away from positive, away from positive, and away from positive. And I've only got one negative here to kind of show you, but they go towards negative, and the arrows indicate the direction of the electric field. And you can almost think about it as like flowing water, right? The electric field lines not only tell us where the positive and negative charges are, they also offer a little bit of insight about the strength of the field. And so where the lines are close together, right, down here, where the lines are close together, that tells us that the electric field is very strong at that point. And so, like in this bottom picture, for instance, I see lines very close together here, very close together here. And so the electric field is very, very strong at those points. Where the lines are farther apart on electric field, like maybe this big empty area here, the electric field is very, very weak. Or, for instance, here, those lines are farther apart, and so the electric field is very, very weak. So let's have a little pop quiz, right? A set of electric field lines is directed as below. At which of the noted points is the magnitude, and this just means size, right, or absolute value, of the field the greatest? And so is it the greatest at point A, B, C, or D? And so based on what I just told you, lines close together means strong field. Lines far apart means weak field. And so we would select A is the strongest electric field there. As kind of an extension to this, what is the charge right here from which this electric field is emanating? Is this a positive charge or a negative charge? And so to decide that, I would look at these arrows. They're flowing away. Therefore, I know that this electric field is coming from a positive charge. They might be going to a negative charge, but if it is, it's very far away, because all I see is this getting weaker and weaker, not coming back around like it would in a dipole. So like in a dipole, D-I-P-O-L-E. Dipole is just when I have two opposite charges right next to one another. Okay, so I can assume this is from a positive charge, and A has the strongest electric field. And that makes sense because A is the closest. Right? So at which, same picture, but at which set of points is the magnitude of the field the smallest? So where is the smallest electric field? And well, the weakest electric field is where the lines are far apart. And so we're looking at D as being the weak version there. All right, so let's say positive charges create an electric field in the space around them. In which case is the field at the black dot the smallest? Right? And so, at which case is the field, the black dot, the smallest? So I have two situations where I've got like a +1 column, and I've got two situations where I've got like a +2 columns. Right? And I need to think about where is the electric field the smallest. And so if conceptually you're not really sure about this, you can always fall back on your formulas to help you, right? And so I can say, I know the electric field is equal to K, Q over R, and I know K is a constant, so I'm just going to kind of neglect that conceptually because it's the same for every single one. Let's say Q is 1 and R is 1, right? So the electric field for A would be 1 over 1. It should be 1. And the electric field for B would be 2 over 2, which is also 1. The electric field for C would be 2 over 1, which is 2. And the electric field for D would be 1 over 2, which is 0.5. And so D is our winner, weakest electric field for that, right? And so if you're ever not sure, try and fall back on your formulas and think about it conceptually that way. Okay. There are both uniform and non-uniform electric fields. A uniform electric field is where there are even spacings between the field lines, right? And so the field has an equal strength at any point here. So the electric field strength here is the same as here, is the same as here, is the same as here, and I can tell that by the spacing of the field lines. There are non-uniform fields as well, so things like here where the spacing is different, and the electric field strength here versus here versus here versus way out here is all very different, right? Same here, there's variable strength in this electric field. And so when we consider things like dipoles or point charges, those are usually not uniform electric fields. And so particles can kind of behave unpredictably in those. To talk about non-uniform electric fields, I'm going to consider my dipole that I have here with the positive charge up here and the negative charge down here. And what I'm going to do, there's a variable electric field here, and we can kind of see the field lines. It's strong right at this point, and it's very strong right at this point. What I'm going to do is play this, and these two charges actually exert a force on one another, and so we're going to see how that plays out, right? And so this can be, after a short while, pretty unpredictable about where these charges are going to go. For us as humans, we want to control electricity, and so uniform electric fields are much more useful for us because we can predict what's going to happen. There's not this huge variability in that field. And so when we talk about uniform fields, this is where if I place a charge anywhere, it is going to behave exactly the same no matter where I put it. And to get these uniform electric fields, we use a device called a parallel plate capacitor. Right? And so parallel plate, these are just two thin metal plates. Let's see. So these are just two thin metal plates, and they usually have some kind of a wire connected to them to charge them, so either from a battery or a wall outlet. And what we do with these plates is we charge one with excess positives, and we charge one with excess negative charges. And again, that creates an electric field that flows from positive to negative. We say that this plate overall has a charge of Q, and again, Q is just in columns, but it's equal and opposite. So like if this has a charge of 4, then it's +4 up here, +4, and it would be like -4 down here, right? There we go. To get the electric field within a capacitor, we use the following formula. And so if we want to calculate the electric field strength in here in this uniform field, we will use the charge of the capacitor multiplied by our electrostatic permittivity constant and the area of that capacitor. And so if I'm dealing with like a square capacitor, then A is just length times width. If I'm dealing with a triangular capacitor, then it's 1/2 base times height. And if I'm dealing with a circular capacitor, then I'm going to be looking at pi r squared. And so it'll be important in this A to kind of pay attention to the geometry of the capacitor that you're dealing with. Most of them wind up being squares or circles. Triangles are very, very rare. And just like K was a constant, our electrostatic permittivity constant is a constant as well, and it's just the set number that you use every time. And so what we find is that if the charge on a capacitor increases, then so does the strength of the electric field. If the area of a capacitor decreases, then so does the strength of the electric field. Okay. Really quickly, kind of as a little side note, and we're going to play with this next week in lab, cells have electric fields as well, and your entire body depends on kind of this parallel plate capacitor thing. When we have nerve cells, you know that nerve cells send electric signals from your brain to your muscles. And so what happens is they actually exchange ions. And so we talked about this last class, that an ion is something that that loses or gains an electron and has an overall net charge. And so what your nerve cells will do is they'll actually pump sodium and potassium into and out of the cell to create an electric potential and then kind of an electric field across that. What that does is that it ends up allowing your cell to send that electric signal on. Once it gets to the synapse of like a nerve and a muscle, these neurotransmitters are released and calcium floods into your muscle cell to allow it to contract. Right? Your heart is also an extremely important muscle that depends on electricity for it to even work. And so what we see is that in a heart, your heart actually has its own electric field. And if you've ever been to the hospital and had that little thing clipped on your finger, boop, 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 that is actually measuring the strength of the electric field of your heart to make sure that it's beating properly and that the entire muscle is acting as it should, with that membrane potential, sodium and potassium kind of spreading across it, beat to beat. So every single beat, your heart will polarize and depolarize and then beat again, right? And always in this direction. And so we see the first polarization happening here. This polarization will move up, it will move up here, and then the entire thing will decharge and it'll do it again every single beat. Right? And so this is what an EKG is. Actually measure the strength of your electric field and telling us, right, when those kind of peaks of positive and negative charges are happening. We can analyze and say, okay, this is a normal heartbeat. This is normal, but it's fast, and this is normal, but it's slow. And then for an irregular heartbeat, this is a big concern because what we see is that there might be damage to a tissue in like a ventricle where that ventricle isn't completely contracting or it's not passing on that electric signal like it needs to, and that's resulting in an irregular heartbeat and probably irregular blood pressure and distribution of that as well. Right? The last note that we're going to talk about in class, we talked about, okay, well, metals are conductors, right? And so if you're in a big airplane, whoop, and let's see, that's going to be my airplane. Whew, don't judge me. So if you're in a big airplane and it gets struck by lightning, well, why doesn't that mess everything up inside? And so when a conductor is in electrostatic equilibrium, there's no electric field in that conductor. And so what we see is that when lightning strikes a plane, it actually gets distributed all throughout the outside. But, well, good news, the electrics of a plane are inside, and inside the net electric field is 0. And so if a plane gets struck by lightning, or if a car gets struck by lightning, or any kind of metal sphere gets struck by lightning, then, well, those charges move all along the outside of that. But for objects inside, it's okay, you're safe. The electric field is 0, you're not going to get zapped. Right? When we draw field lines, we draw them perpendicular to a surface. So this is kind of a zoom in of, let's say, my plane. Let's say I'm riding through a storm, and I've built up an excess of positive charges on the surface. Well, then there is an electric field emanating out of that. And the important thing about this is that these field lines come out perpendicular to the surface wherever they're at. And so you'll never see an electric field line that's like this, right? It's always got to go perpendicular to the surface. So what I'd like you to do for a second is draw a triangle on your paper. And we're going to do a triangle because it's more or less the shape of like a human or a tree or somebody playing golf. and what I want you to do is, let's say there's a storm coming, and this person might not realize it, but there are positive charges building up on the outside of them. Okay, and so I'm going to draw some little positives here. What I would like you to do is take a second in your triangle and practice this whole 90-degree thing. We've got some clouds up here, and draw these electric field lines coming out of this person or our triangle, and draw them at 90 degrees to the surface. And I want you to go all the way around both sides and see what happens. And I'm going to go ahead and do it on mine, but I'm going to do it in blue. So let's see. 90 degrees, 90 degrees, oh, 90 degrees. So the pattern here that we start to see emerging is that the electric field is very strong. Right at the top, we wind up with all these lines really close together. And so this is important if you're ever hiking and a lightning storm comes up on you quick in the mountains. Pointy objects have a stronger electric field on them. And so as part of lightning safety, what we teach you is to do the lightning crouch and make yourself round instead of pointy. And when you're round instead of pointy, those field lines are a little more evenly spaced and not as strong. And so when that potential builds up, if you have a very strong electric field right here, well, then you're more likely to get zapped by lightning because it is attracted to that strong electric field that you are emanating. If you are a rounded object, well, then you're not as likely because your electric field is not as strong. And maybe it'll go for like the pointy rock out to the side, or that tree that's standing up, right? And so this is why trees often get zapped by lightning, because they have this pointy shape and they build up charges and they get that really strong electric field right towards the top. This is a really great example of this, right? And so we've got Statue of Liberty, which is extremely pointy. And when you look at where this is striking, well, it's striking right at the hand, right? The very pointiest pointy part of the pointy statue, because that's where the electric field is the strongest. And so for your homework, I would like you to try a few conceptual problems, okay? And then we will work on quantitative problems in class.